Hey, everybody. I'd like to welcome you to the Audio Programmer Meetup. This is the September 2023 edition, and we have another promising lineup as always. We have a newcomer, Damien Ronnsin, who is over in Switzerland. He works with minimal audio, and he submitted a plugin called NeuralNote in our Neural Audio Programmer competition earlier this year, and he's back to talk a little bit about how he created that using Spotify's pitch model. How are things going, Damien?
Very good. Thanks for inviting me, Josh. Very good.
No problem. And we have somebody who's not so new to the Audio Programmer Meetup, Jatin, who is giving another talk today about buffers and running your own buffer class from scratch. So he's tuning in with us all the way from Seattle. How are things going, Jatin?
Hey guys, yeah, doing well. Thanks for having me again.
Yeah, no problem. So as always, wanted to remind you about the Audio Programmer community on Discord. So we're coming up towards 10,000 members now on the Audio Programmer Discord, and you can always join us on the audioprogrammer.com/community. We also have development and recruitment services. You can find out more about those on our website, theaudioprogrammer.com. And with that, we'll just go ahead and jump straight into the talks. We're going to go ahead and start off with Damien. And Damien is giving a talk talking about NeuralNote and how to get a machine learning model into an audio plugin. Over to you, Damien.
Yes. So let me share the screen. And here we go. All right, so hello everyone. So I'm Damien, and I'll present to you today NeuralNote. So it's my contribution to the Neural Audio plugin competition, and we'll talk about how we can integrate a machine learning model in an audio plugin, basically. So first, a few words about me. I'm an engineer. I have a master's degree from EPFL in computational sciences. I'm based in Lausanne, in Switzerland. And regarding my professional background, I used to do some machine learning research and development on speech processing before at Logitech. And now I'm a DSP engineer doing some pretty exciting plugin development at Minimal Audio. Stay tuned for the coming product. It's going to be great. So now about NeuralNote. So as I said, it's an open source audio plugin that does audio to MIDI, and it's based on Spotify's BasicPitch. It's a model that they open sourced that does automatic music transcription. And it was created during this Neural Audio plugin competition. So thanks again to Josh and Andrew and Christian for organizing this competition, because that's really what gave me the motivation to get started on this project that I had in mind for a bit of time. So thanks for this. And also thanks to Tibor and Perrin, who were my teammates for this competition. Tibor for the development side and Perrin for the design. And since it was released, I think it was in April this year, the repo got quite a bit of interest with more than 500 stars on GitHub and more than 30,000 downloads. So I'm pretty happy about this, pretty surprised as well. But it seems like having audio to MIDI right in the door using machine learning, it's people interested in that. So now for the plan, I'll start directly with a demo of NeuralNote, so you can see how it works, what are the different features. Then I'll explain the basic pitch architecture, what are the different components of the model, and then I'll explain how I implemented it in the plugin, how I ported it to the plugin. And this will be the base for a discussion on how we can have neural networks in audio plugins in general. Then I'll present quickly the other NeuralNote features, and finally I'll go through the roadmap for the future features that I'd like to have in NeuralNote. Before jumping to to the demo. A few words about BasicPitch. So it's a model that research team at Spotify open sourced. The team is called the Audio Intelligence Lab, and yeah, they open sourced the code under the Apex 2 license. And their model is really great because it's instrument agnostic. It works with any tonal instrument, including voice, which is pretty sweet. It supports polyphonic transcription, so you can play chords, you can, it will pick up everything. And it also supports pitch bend detection, which is nice because it adds some expressivity to the transcription. So now let's jump into Logic. So I have a track that is ready. And if I go here, I have NeuralNote. So this is the plugin. I'll delete the transcription that is already there. And the first thing you need to do with the plugin is to gather some audio. So let's play and hit record. You should be able to, if not, but you should. So I'll mute now the guitar. Just so that I can explain while it's recording. So once the recording will be done, automatically the transcription will be launched, and under a second we will get the transcription here in this piano roll section, and we'll be able to play with the different parameters to adjust the transcription, and we'll even be able to play with the parameters while listening to the transcription, which is nice. And it's a new feature that wasn't in the first release that I did for the competition. So yeah, okay, so we're arriving at the end of the recording. And you see directly we have the transcription here, and we can listen to it. Here we're both the transcription. I can turn down the guitar, and we can see that it's pretty good. This part. And now I'll explain a bit the different parameters that we have. So first we have a note sensibility parameter that if you turn it up, you get way more notes that maybe shouldn't be there. It's too much, but if you bring it back something reasonable, it depends on the instrument you have, on the audio clip you have. So it's important to tune it. And then what I like to do is turn this split sensibility down so that it can merge like different notes that are very close to each other together. Usually like it stops a note and starts a new one right after. So it's nice parameters to have. And finally, we have this minimum note duration to get rid of the very short notes here, and we can remove them. Then some basic functionalities about scale quantization. If you have a specific scale, you can also limit the range of the audio of the notes. Choose a key. And then a nice thing, it's the time quantization. Here I've recorded with the DAW, so I have like the tempo information that was detected, and I can snap on the grid, which give a way better result because the onset detection is perfect. And once I've done all those settings, adjustments, I can just drag the MIDI file from here and drop it here. And now have it on a piano and have time. So I think you can get pretty creative with this. It can simplify your workflow if you like to dub things with other MIDI instruments and you don't have you just have an audio file at the beginning. You can transcribe it and then play it with different sounds. So that's pretty nice. And I have a few other examples just to show here with a voice sample. So if I mute this, we can listen to the voice sample. And we can replay it, just a transcription that I did before. So it's working pretty well, even with voice. So that's nice. And one thing also that I like to do with NeuralNote is to learn new song. Like I have, for example, here a piano track that I want to learn, and I don't have like perfect pitch or anything. So I can go and take the file directly instead of recording, just dropping it on the track, and then I have the transcription right away. And I can drag it again on the piano track, sorry, and we'll have it. It's not perfect, but you can always adjust, and to learn a new song, it's pretty nice. So that's it for the demo. And let's go back now to the presentation. What I can do really quickly is show you also the demo from BasicPitch, because that was kind of a big inspiration for me. They've created this website where you can do like the same thing, drop your audio file and get the transcription, play it, and so on, adjust the different parameters. So this was a big inspiration, but I really wanted to have it directly in the DAW, so you don't have to upload a file. And I wanted it to be snappier as well. So yeah. Then where are my slides here? Then let's dive in the architecture. As input, of course, you have your audio signal. So it's just a one-dimensional array with num samples, a given number of samples inside. And the first thing that is done is to convert it into some features. Here they use the constant Q transform. So it's kind of a frequency domain transformation, similar to an FFT, but also a bit different. I'll explain a bit later how. And then this is given as input to a convolutional neural network that will provide 3 different probability matrices, time frequency matrices, the onset, the note, and the pitch probability matrices. The first one, it will really tell you for a given frame, so a given point in time and a given note. Here, the 88 dimensions, it stands for the 88 notes that we have on the piano, like from A0 to C8. And for a given point in time and a given note, it will tell you this is the probability that this note starts now. So it's really about the onset. For this matrix, it will tell you for a given time and also a given note, the probability that this note is playing at this given time. And with those 2 matrices, you can create note events. So the start time, the end time, and the pitch of the note. So you really have MIDI notes here. And then if you combine it with the pitch probabilities, that is also a probability matrix, but that has a better frequency resolution. You can get more like a pitch curve, and you can get like a better more details on the pitch curve and generate pitch bands oscillating around those notes. And with that, you have the full MIDI transcription. To generate the notes, also, we use some thresholding parameters, some sensibility parameters, the ones that I showed before in the demo. So first, let's talk more about the constant Q transform. So as I said, it's similar to an FFT, but it's different in that the frequencies, they are not linearly spaced. They are spaced logarithmically, but just like musical notes. So that's why it's very useful here. And they chose like to have a resolution of 3 bins per semitone. So you have 88 notes that we want to transcribe times 3, and this gives you the 264 bins. And they do that for frames that are taken every 11 milliseconds. So you get a time frequency matrix again of that shape. And finally, they do a last step called harmonic stacking that consists in stacking harmonics over a third dimension so that the harmonics are closer to each other in the input tensor that is used by the convolutional neural network. Talking about the CNN, here we are. So on the right, you have the full architecture with all the layers dimensions. So as you can see, it's a bunch of 2D convolutions with some batch normalization and some activation functions. And we can see the three matrices, probability matrices as output here. And I think it gives an intuition about what they are. So here we have the onset matrix. So it really goes bright only when a note starts. Then we have the note probability matrix that really looks like a piano roll, like it's almost the MIDI that is ready. And this tells you when a note is active. And finally, we have this contour or pitch matrix that really looks like a pitch curve, and that gives you more detail. You see here we have a note that doesn't change, and here we have the vibrato here that we can use to generate the pitch bends. The 2D convolution, so of course the kernels are acting both on the time and frequency axis, but as the convolution are non-causal, it means that there is some look ahead, and this will have some impact on the latency. We'll talk about that later, but here, if you compute regarding the size of the kernel on the time axis, you can see that the CNN has 12 frames look ahead. So this will introduce some latency, but I'll talk about this later. Finally, the last step is to create the note events from those probability matrices. Each node event is defined like this. You need to have a start time, end time, a MIDI note, a pitch, and then a pitch bend array. And those are all computed by doing some thresholding operations on the probability matrices. So now let's talk about latency, because it's quite a I had a lot of requests about this on the NeuralNote repo. Like, could this work in real time? Could we have a BasicPitch transcribing my music in real time? And unfortunately, we can't, because we have too much latency in the different parts of the algorithm. As I said, the CNN has 12 frames look ahead. So this means more than 100 milliseconds look ahead. And if you've done, or even if you used some plugins or your plugins before, you know that this is already way too much if you want to have something really snappy. But when I started the project, I knew about this 12 frame look ahead thing. And I was like, okay, I'm still gonna try to do something in real time, because even if it's not directly, we can reuse it very fast to trigger different things, for example. But the main issue is with the constant Q transform, because I didn't know it when I started the project, but it's different from an FFT because the CQT uses different frame sizes for different frequencies, and it will use huge frame sizes for low frequencies in order to have a good resolution in the low frequencies. And like huge frame sizes, it means more than 1 second. And this adds to the total latency of the algorithm. And so if you have something with 1.5 seconds of latency, it's not even worth it. And to finish with the impossibility of doing transcription using BasicPitch in real time, the node event creation currently is non-causal because the probability matrices are processed backwards to create the nodes. So from the end of the signal to the beginning. And so this has kind of an infinite latency. But I think that this could be changed because it's kind of an handcrafted algorithm. And I think we could find something, come with something that is more or less equivalent and that process thing with less latency. So that's it for the real-time question. Now, how is BasicPitch implemented in NeuralNote? So as we're processing everything offline, everything is running on a background thread. For the CNN part, I chose to use RT-Neural, so from Jatin, that is also here. I chose this because at the beginning, as I said before, I didn't know there was that much latency in the whole algorithm. And I wanted to have something in real time, working real time. So I decided to go with RT-Neural, and I needed to have 2D convolutions in RT-Neural in order to run BasicPitch. So I contributed to RT-Neural by implementing this layer. I only did the eigen backend. Thanks, Jatin, for doing the rest. But it worked in the end. And the way it is used, it's running in streaming. So it means it's running for every frame. The CNN is running for every frame. And it has the nice property that it's running with a constant memory usage. For the constant Q transform, surprisingly, I had to use a machine learning inference library. I am using ONNX runtime. It's surprising because the CQT is just a DSP operation. It's a cascade of filtering and downsampling stuff. So it's not usually done with neural network operators. But in the BasicPitch repository from Spotify, they implemented it using TensorFlow. And so converting to ONNX and running it with ONNX runtime was the easiest thing to do on my side, because the algorithm to compute the constant Q transform is quite elaborated. But this could be done in plain C++ as well. And the way we're running here, we're not running in streaming, but it's executed once for the whole signal, for the whole audio we like to transcribe. So now that I have this, let's have a little comparison game. Is it better to use ONNX runtime or RT-Neural if you want to have a neural network running in your plugin? I'd say it really depends on what you're trying to do. So let's compare point by point and then summarize at the end. So ONNX runtime, if you don't know, it's a library that is maintained by Microsoft. It's a pretty big library because it aims at supporting not just a specific field of neural network, but all fields. You can run LLMs with ONNX runtime. So it supports many layers, if not all. And on the other hand, RT-Neural, it's a very small library that has the common layers that are used in audio processing. So convolutions, LSTM, GRUs, and dense layers, plus some activation layers as well. But as I did, if you need to have something, if you need something specific, you can always jump in the code and implement your own layer. It's pretty easy because the library is small, well documented, well written. So it's easy to jump in and implement your own stuff. I don't know if that's the case for ONNX runtime. It's a huge library that supports many execution providers, it can run on CPU, on GPU, and stuff like that. So I don't know how easy it is to integrate your own custom layer. Maybe they have something specific for this, I don't know. Then to get it built and link with your project, for ONNX runtime, if you want to run it in a plugin, it's quite a bit of work because ONNX runtime doesn't provide a straightforward way to compile it as a static library. And so for that, I had to use ORT Builder by Oli Larkin that I think presented this library in the previous meetup. So thanks to him for creating this because it's really handy. But still, even with this, it's a bit of work to get built as a static library. And for RT-Neural, it's very easy because you compile it alongside your project and it works out of the box. Now comes the main difference, the main thing you have to consider if you have to decide between those two libraries or those two kind of libraries is the statefulness. So ONNX runtime, it's stateless, and it means that in between two execution of the model, it forgets everything. It doesn't remember, it doesn't keep the state inside the model updated. And that's a problem if you need to do some streaming processing, like in an audio plugin, you have your buffer in, your buffer out, and you have to keep running. There are some solutions. You could add your states as input and output to the model and then pass them each time that you run. But it works well for RNNs, but for streaming convolutions, as I'm using in BasicPitch, it's not great. But BasicPitch is not running in real time, so I could have used ONX runtime for everything. But if you need to have audio to audio, this can be a problem. On the other hand, RTNeural is stateful, so it's really made for that. The model is made to run for every sample that you have or every frame. And if you need to have an effect, audio to audio effect, or this is a really nice thing to have, the statefulness. Now, concerning the conversion from your training environment from PyTorch to TensorFlow, it's very simple using NeuralNote runtime because all the layers are supported and everything. It's a bit more work to do it with RTNeural because you really need to know very well your model to be sure that all the layers are supported, that there are no that the dimensions of your tensor, they are laid correctly in the right orders and so on, so that you have a smooth export. But it's completely doable. You just need to be a bit more careful about it. Then concerning the real-time safety, I'd say both are real-time safe. So Jatin, correct me if I'm wrong, but you said, I think one time that you tried to determine if ONX runtime was real-time safe and you couldn't really figure out if it was the case because doing some stuff with threads and memories that it's a bit hard to follow, so you really never know. But I used ONX runtime in real-time context, and it was working pretty well. Never encountered too many bad stuff. And then for RTNeural, of course, it's real-time safe. It's in the name. So yeah, and then concerning the performance of the libraries, both are very optimized. But according to Jatin's benchmark, RTNeural is faster than ONX runtime, especially for small layers, and that's we usually use in audio plugins. So again, it really depends on what you need to do. If you want to emulate an effect using neural network, I think RTNeural is definitely the way to go. But if you need to run some offline processing with complex networks with many layers, many different stuff, I think going with ONX runtime is easier because morphing is supported. So that's it for the comparison. Then some words about the other features that are non-ML based in NeuralNote. So I recently implemented an internal synth so that we can listen to the transcription right in the plugin without having to export the MIDI and then listen and then adjust and then re-export and so on. So that's a quite nice feature, but it's just a simple ADSR plus some sinusoiders with some harmonics. It's not sounding great, definitely not. So I'd like to get some improvements here. And also there's an audio player. You can replay the audio that you recorded at the same time as the transcription with independent gain control for both the source and the transcription. For the parameters, I already showed that in the demo, so we can adjust the transcription parameters and do some quantization on the scales, on the notes, and on the timing of each note. And to get some audio in the plugin, we can either record or drop a file or browse a file in your file system. So actually, this is Jatin that implemented this. Thanks for this contribution. And then finally, the roadmap for NeuralNote. So regarding the enhancements, I need to have a better parameter and state management because for now, the plugin forget everything every time you reopen it. So it's a bit of a pain sometimes. So that's really my first priority. Then I had a couple of requests about being able to stream MIDI out of the plugin so that it can be routed to another instrument. I don't know how doable it is with the different plugin formats, if it's supported everywhere, but it's definitely something that would be nice and that I'll try to make happen for the things, where it works. I think for VST, it's doable. For audio units, it's a bit, I don't think if it's possible. I don't know if it's possible, but I'll try. And then also a couple of requests on Linux support. So I'll try to get a Linux build out there. And for longer term, I have some ideas. So one thing that I think would be nice is to have some more machine learning inside the plugin and have source separation models so that you can drop a full song in NeuralNote and then say, okay, I just want to transcribe the piano. So you first run a source separation model for the piano, you get the isolated piano track, and you run BasicPitch on this. Also, so I think this would be pretty nice. It would give you more possibilities in NeuralNote. Then I'd like to have more sounds and better sounds for the internal synth. I don't know how I could do it in a simple way. So I'll think about it. And I'm thinking also about adding the capability of editing the MIDI, but I'm not sure because it would be a lot of work and you can already do this in your DAW. So I don't know if it's worth it adding it. But anyway, if you'd like to contribute to any of those things, or even other things that you would like to see in NeuralNote, please do. It's open source, and I try to be as responsive as possible for the contributions and the issues on GitHub. So don't hesitate to reach out. And that concludes the presentation. Thanks a lot for listening. Thanks a lot, Josh, for inviting me. And if there's any question, I'm happy to answer. Thanks.
Great. Thank you very much, Damien, for that amazing presentation. A lot of really positive comments in the live chat. And I'll just read a couple of them. And if you have any comments, please feel free to remark. So one is from Matthew Yi King. Hi, Matthew. Good to see you. He says, emitting MIDI would be great. I have a plugin that learns and regenerates MIDI patterns that would work really well with this on live instruments. Yeah. And he had asked if this is the first time Onyx and RT Neural had been combined on a plugin. Any thoughts on that, Damien?
Don't know. Maybe because it's quite unusual. Like if I knew that the plugin that BasicPitch wasn't running in real time right from the beginning, I think I would have just used only Onyx runtime. But in the end, I'm very happy to have used RT Neural because I learned a lot while contributing for the 2D convolutions. I really learned a lot by just going through the libraries. So yeah, quite happy to have done that choice in the end.
And there's a question from Angel who asks, can this model be used to detect percussive sounds such as beatboxing? If not, how would you go about doing that?
No, it can't. It wasn't trained for that. But I don't think it's the right architecture to do this because it's very different from tonal instruments. But so you would need to take another approach to this. But definitely it would be super nice to have like another model that would detect percussive sounds and beatboxing, because you can get really creative with that as well.
Right. Angel also asks, can the model be further fine-tuned with more data? For example, if we want to improve the model for guitar to MIDI transcription.
Yes, you could fine-tune the model, but I don't know. This we would have to look on the BasicPitch repository from Spotify. I don't know if they shared the code to train the model, but if you have some data, you can always load the model and keep like training it. Everything is described in the paper, the loss function, stuff like that. So that's I think you could get some better performances if you want to fine tune to a specific instrument for sure.
Fantastic. And I think that's all the questions we have for now. I'll give a couple more seconds for people to ask. And thank you very much, Damien. That was really awesome presentation. Sounds like you put a lot of work into that. Did you, for the piano roll, is that a web view or did you actually do that in C++?
I'm drawing rectangles in Juice. No, yeah, it's not as hard as it looks, but yeah, it was quite a bit of work.
Great. So we have a question from Ana Paula Ramos Lopez, who asks, would this action pose potential intellectual property concerns? Are there any legal ramifications or potential infringements associated? Any ideas?
Yes, because I mean, I have some ideas. I think that in the data they use to train BasicPitch, it's all open source things with the required licensing and so on. So I think on this side we're good. And one thing I didn't mention about BasicPitch is that it's a very tiny model. It only has like 16,000 parameters. So you don't need a lot of data to train it. So you can get something that works very well even with this small amount of data. And that's also why like this model is fantastic, because it's not like overkill. They just did the right choice for the features, for the loss functions, the way they did it. It's not just putting a big neural net that does everything. They really thought about how we can do things properly and have the correct features and so on. So yeah.
Great. Looks like that's it for questions. Thank you again, Damien.
Thanks.
And for anybody who's curious about the slides, you can actually check out the slides. They're linked in the video description, as well as Jatin's slides as well. And with that, we'll go ahead and we will pass the mic on to Jatin. So Jatin is going to talk to us about buffers. The title of this talk is called Audio Buffers, Buffer Views, and Buffer Iterators. And Jatin is the founder of Chowdhury, which is he does a lot of open source projects and also knows a lot about analog modeling as well. And with that, I will go ahead and pass it over to Jatin. Take it away.
Yeah, thanks, Josh, and thanks, Damien, for your presentation. I've been a big fan of NeuralNote for a long time, as you know, so it's cool to see the project have come so far and to hear about all the steps along the way. Yeah, it's a great project. Yeah, so today I'm going to be talking mainly about audio buffers and things that you can do with them and how to create your own if you have a need for that or if you want to do that. Just a little bit about me. So I'm an audio developer in Seattle. Previously, I was working at Tesla, and before that, I was studying at Karma. And nowadays, I mostly make plugins. I use Juice and various other tools. So kind of what I'm going to talk through today is first just talking about containers in C++ and kind of the different things that they do and the different features that they have. I'll talk about building up your own audio buffer essentially from scratch, but really starting from the C++ standard library. And then I'll talk about a few other sort of auxiliary things like buffer views, buffer math operations, and then buffer iterators. And yeah, hopefully it'll be fun and we'll learn some things along the way. So starting off just with C++ containers, I'm going to define a container as just something that gives you access to multiple other things. Usually they're all the same type, but I guess maybe they don't have to be. And if you're talking to C++ people about containers, they'll usually separate them between contiguous containers and associative containers. And the idea is that a contiguous container stores all of the items that your container holds in a contiguous block of memory. So your first item is living in some memory, and then the next item is right next to it, and so on throughout the length of your container. With an associative container, that might be something like a set or a map where things kind of live all around memory, but then they're able to point to each other or access each other through various means. For today's purposes, we don't really care much about associative containers, but I think it's good to mention them just to know that they're there. For today's purposes, I think it's more useful to split our discussion between owning containers and non-owning containers. This is kind of my own definition. I think there's other definitions as well that talk about the same idea. But the idea with an owning container is that the container manages its own memory. So if the memory is allocated on the heap, then when the container goes out of scope, it will free that memory. Or if the memory is allocated on the stack, then that memory will be invalidated when the container goes out of scope. Typically, if you need to pass an owning container to a function, you're going to pass it by reference because most of the time these containers can be expensive to copy. And when you make a copy, the copy is going to refer to some different memory than the original. So if the idea is that, oh, I'll pass my container into this function, and then the function will modify the stuff inside the container, that doesn't really work if your copy refers to a totally different chunk of memory. So some examples of this, I'm sure everyone's used them, are standard array, standard string, and standard vector. These are all kind of your classic owning containers. With non-owning containers, these are usually things that you'll see labeled as a span or a view in kind of the way they're named. And the idea with a non-owning container is that the memory for that container is managed somewhere else. And I'll give an example of this in a second, but it's useful to know that if you're using a non-owning container, you're responsible for making sure that the lifetime of the container doesn't go past the lifetime of the underlying memory. With a non-owning container, they're usually very cheap to copy. So people usually pass them by value. And when you make a copy, it still refers to the same data. And again, I'll give an example of this in a second here. So some classic examples of non-owning containers are string view, which was added to C++ in C++ 17, standard span in C++ 20, and then MD span, which will be coming in C++ 23, or maybe you already have it if you're kind of on the cutting edge of C++ compilers. So this is kind of your most basic implementation that you could have for a standard span. I'm sure the real implementations in Clang and MSVC are probably a good bit more involved, but the basic idea is that you have some pointer to your data and then some integer-like value to keep track of the size. You could also do it as like a begin and end pointer or something like that, but it's kind of the same idea. You just need to know where does my block of data start and end. And as you can see, this is a very small class. It has a very small memory footprint. You could copy it. You could pass it around to different functions, and it will be cheap to do so. So a little example of using a span. So in this case, we have a function, and the idea is that we want to take some span of integers, and we want to add 1 to all of them. So what we could do is we could have, for example, a vector, and we can pass the vector to the function, which will implicitly convert it to a span, and it will do the operation and modify the data in the vector. We could also explicitly construct a span and pass that to the function, and that works fine as well. But then what we need to be careful about is that if we, for example, here we could free all the memory in the vector, Now, if we try to do something with the span that we had created, then we're going to get a bad memory access because the memory that the data view expects to be there is no longer there. So that's something to watch out for when you're working with non-owning containers. I want to give another example just to show how like constness works with non-owning containers. So here we have a function that's going to take two spans of integers, add them together, and put the result in some other span. And so here, again, since the spans are being passed around by value, what we need to do is make sure that the constness of the container applies to the type in the container, not necessarily to the container itself. So if we were to make this a const span of ints, that wouldn't really mean anything because we're making copies of these spans when we pass them into the function. So being const or not doesn't really matter so much. Really what we care about is that the data inside the span is constant. And so that's how we make it clear to the compiler that that's what we want to do. And then in this case, we're going to use arrays just to show that arrays can also be implicitly converted into spans. So that's kind of how you would use a non-owning container in more general C++ code. And again, just some guidelines. If you're the user, you're responsible for managing the lifetime of the container relative to the memory that it's referring to. In most cases, there will be an implicit conversion to go from some owning container to a non-owning container. And then if you want something to be const, make sure you're applying that constness to the type and not to the container itself. Being that we're doing audio programming, we also want to know about memory allocation and where that fits in. So if you're just kind of going through your C++ containers and you want to think about when it will or won't allocate memory, if you're using a standard array, that will never allocate or deallocate memory on the heap. If you're using vector, it's very specific in the C++ specification when vector will or won't allocate memory. So here's kind of a simplified version of the rules for when vector will allocate memory. There's a lot more nuances to this, but if you care about that, you should go read the spec for it. On the other hand, something like standard string is a lot less specific about when it will allocate or not allocate memory. And this is, at least to my understanding, mostly because of the small string optimization, which could be more implementation defined rather than specified by the C++ standard itself. And then the non-owning containers in the C++ standard library will never allocate or deallocate memory. So that's always a good thing to know as well. So yeah, that's just kind of a brief overview of some containers in C++ and how they're put together and how they can be used. And so now we can talk about creating an audio buffer. And so this is something that I started doing about 1.5 years ago when I was working on a project that I kind of needed an audio buffer for. And so I started thinking, okay, well, what do I need my audio buffer to be able to do? And so for now, I want to make an owning container to be my audio buffer. Later, we'll talk about a non-owning kind of version of this container as well. And so kind of to start, I was thinking, well, okay, I want sort of a two-dimensional data structure that holds a bunch of samples. So usually these will be floats or doubles, but maybe it could be other things too. I want it to be dynamically allocated and resizable. So basically, I don't want to have to know the size of the buffer at compile time. I want to be able to have it be determined at runtime. And then I want to be able to shrink the buffer without reallocating memory. So something that happens a lot in my code is like, okay, I know that the maximum block size for whatever audio process I'm going to do is like 256, but it could be used with a smaller block size, like 128 or something. So I want to be able to shrink the buffer from 256 to 128 without reallocating memory, and then grow it back to 256, still without reallocating memory. I guess if I wanted to go past 256, then that would require reallocating memory, but that's something that I have to pay attention to as the user. And so my first thought was, well, I could just use like a type def, so I could have my buffer class just be a vector of vectors. And the reason why I didn't do this is, first of all, with an audio buffer, we usually want all of the, we would want all of the vectors, all of the inner vectors to have the same size. Because typically you have some number of samples, some number of channels, and depending on which way you store it, whichever one is the inner size, we want to be the same all the way through the buffer. And you can't really have a hard guarantee on that if you're doing a vector of vectors like this. And so that kind of made me a little bit wary about doing it this way. And then I also wanted to have a little more control over the memory layout, which I'll talk about in a second here. If you're right on top of the latest in the C++ standard library, you might say, well, why not use standard MD span or MD array? And at the time, those didn't really exist yet, or at least I wasn't aware of them. It seems like those would be really good candidates for doing this kind of stuff now. And if folks are using MD span or MD array for audio buffers, I'd be really curious to hear your experience and to see how those are working for you. But yeah, MD span is in C++ 23, and MD array I think is going to be in C++ 26. And yeah, I want to make sure that whatever buffer type I'm using is probably at least compatible with C++ 14 or C++ 11, certainly C++ 17. So yeah, I wasn't quite ready to go for the latest of the latest C++ stuff yet. But again, if you're doing that, I'm curious to hear your experience. So next I wanted to talk a little bit about memory layout. So if you're familiar with matrix math and libraries like Eigen and things like that, you might have heard of this thing where the matrix can be stored in row major order or column major order. And so the example here, we have a matrix that has 9 values in it. And the way that a library like Eigen would store those 9 values is it would create an array or a vector that is 9 numbers long, and then it would store them in chunks of 3. So if you want to do a row major matrix, then you would do your first 3 numbers in the array would be A1, A11, A12, and A13. So you would go across the first row, then you would go to the next row and do those 3, the next row and do those 3. On the other hand, if you want to do column major ordering, the first 3 numbers would be going down the first column and then going down the second column and so on. And so if you're thinking about an audio buffer, you've kind of got the same dilemma, which is, do you want your buffer to be channel major or sample major in terms of how the data is stored? In other words, do you want all of the samples in one channel to be next to each other in memory, and then the samples in the next channel, and so on? Or do you want it to be all of the samples at this time step, and then all of the samples at the next time step across your channels as you go down? For myself, I prefer channel major ordering. So basically you have all of the samples in one channel, and then all of the samples in the next channel, and so on. And the reason for this is that most of the time your buffers are going to have more samples than they're going to have channels. And if you want to do kind of longer vectorized operations, it's usually better to do those along the longer axis of whatever, your data, depending on how your data is stored. I'm sure for some use cases, sample major ordering is better. My guess would be if you have a lot of channels and really small buffer sizes, so maybe you would have more channels than samples in your buffer. Maybe this is true for some like spatial audio applications. Or maybe if you're doing like a polyphonic synthesizer and you want to vectorize across your channels instead of across your samples, then maybe that ordering would be better. I'm just throwing out some hypotheticals. I don't think I've seen a scenario in my own work where I think sample major would really be better. So with that, we can actually start creating our buffer. And so this is like my most basic audio buffer class. So here we have a vector, and that's going to have all of our raw data in it. And then we're going to store the data in that vector. And the amount of data we're going to need is the number of channels times the number of samples. And so that should leave enough room for all of our data. But then I was thinking about it and I was like, well, that's great, but what about alignment? And so the idea with data alignment is that sometimes for vectorization, we want to have your data aligned to some SIMD byte boundary or something like that. And I guess this will depend on like the hardware you're running on and what kind of SIMD instructions you have access to and whatnot. But in this case, the way that I ended up doing it was taking a aligned allocator implementation. I used the one from the XSIMD library, but there's plenty of good ones out there. And then after you align the start of your vector to whatever byte boundary you want, then you should also pad the number of samples so that each channel starts on the same byte boundary and with the same alignment. So that's what I'm doing here with this num samples padded business. So then you could think, okay, well, what if I want a pointer to the individual channels? So if you're using juice buffers, this would be like the get right pointer function. The way that I've chosen to do that for now is to have this array of pointers that I call channel pointers. And then I have some maximum number of channels that I'm allowed to have in my buffer, and that's determined at compile time. And I'll come back to that in a minute. But basically, the idea is that when I set the maximum size of my buffer, I set all of the channel pointers to the right offset in the raw data. And then I can return the channel pointer that I want at any time. And then finally, I want to be able to resize my buffer. So when I set the maximum size and I allocate the data and all that, I just start by setting my member variables for the number of channels and the number of samples to the maximum size channels and samples. But then if I want to resize the buffer at any time, I can just give it a new number of channels, a number of samples, and set those values. And then this is just slide code, but in my real code, I have some assertions to make sure that I'm not going past the maximum allocated size when I resize it like this. Yeah, and then the last thing I might want to do is clear the buffer. And so to do that, I can just fill the vector with zeros or whatever. If I'm using a SIMD type, it'll just be a zeroed SIMD type. And that's it. So that might seem very small, and I promise we'll get to more of the fancy stuff in a second. But just to recap what we've got so far, so we have a dynamically allocated buffer. We can shrink the buffer without reallocating it. We have all of the data in our buffer laid out in one flat block of memory. We have channels that are aligned to some byte boundary that you can choose. We have accessors for the buffer size information and for the individual channel pointers. And we have a function that lets us clear the buffer. And the great thing about setting it up like this is that you can create a buffer with pretty much any data type, so long as that data type is default constructible and can either be copied or moved. So for the most part, you're going to want to do this with a float or a double or something like that. But if you have some cool SIMD type that you want to use instead, again, as long as it's default constructible and can be copied or moved, that should work as well. I tried making a buffer of standard strings. That works. I don't know why you'd want to, but you could if you want. So things that we don't have in this class are any buffer math operations. So like if you want to apply some gain to your buffer or something like that. We don't currently have that. And we don't really have operations for interacting with other buffers. Like if I want to make a copy of some other buffer and have that be this buffer, we don't have a way to do that. And I'll come back to that in a minute and go into more detail about why it's set up that way. So next I wanted to talk about the non-owning version of my buffer, which is the buffer view. So this code looks a little bit ugly, but it's very similar to the standard span implementation that or the example standard span implementation that I talked about earlier. So the idea here is that we have a number of channels, a number of samples, and then an array of channel pointers. And so when we want to create a buffer view from a buffer, we have all these extra arguments, which we can ignore for now, but basically we set the number of channels to whatever it needs to be, we set the number of samples to whatever it needs to be, and then we fill our channel pointers accordingly. If you want to have a buffer view of a const type, you can do that starting from a const buffer of that type. You have to do some funky template stuff, which I don't know that I can explain, even if I wanted to explain it. You'll have to go to Stack Overflow for some of that stuff. But other than that, it works out about the same. You're basically doing all the same stuff from there. And so I set up a bunch of constructors that kind of allow for the same sorts of implicit conversion as you could do with standard span, for example. So if you have a buffer, you can create a buffer view. If you have a buffer view, you can create another buffer view. So that can be like if you need to resize your buffer view, you don't really need a resize option. Oh, my internet browser is freaking out on me here. Okay, sorry about that. Yeah, so you never really need to resize a buffer view. You just create a new buffer view from your old one with different dimensions. I use Juice a bunch, so I have conversions going from Juice audio buffer or Juice audio block into a buffer view. You can also go from some raw data to a buffer view. And then if you have some non-const data structure, you can make a const buffer view from that structure for any of these above types. So that's kind of all of the implicit conversions that I want to be able to do. But I guess if I needed more, I could probably implement more pretty easily. And the idea, like with standard span, is that it should be really cheap to copy a buffer view. And so what I've been doing with this like max number of channels compile time definition is I start with that at like 32 or something pretty big. So if I do need like, some large buffers for like spatial audio or maybe like a reverb or something like that, I can do it. But then usually when I'm close to releasing some software, I'll go through and see like what's the largest buffer that I'm using, and then I'll set it to something smaller. Usually it can do 2 or 4 or something like that. And that just makes everything a tiny bit faster. So that's kind of nice. And so I wanted to give a little example of kind of using buffer and buffer view in tandem. So the idea here is I have some processor that has its own buffer. When I prepare that processor, I can set the maximum size for it. And then when I want to run some process, I can call processor one's process function with my buffer. So this is the owning buffer. And when I write processor one, I can just write that as taking a buffer view and do whatever I want to do to the buffer. And that will apply to stuff in this buffer here. So again, it's kind of like the examples I was showing at the beginning, using standard vector and going to standard span from there. So now we can talk about some buffer math. So if you look at a lot of audio buffer implementations in Juice or various other libraries, you'll see math operations implemented as member functions within the buffer. And I chose not to do that. And the reason why is that, first of all, I've seen that it tends to lead to a lot of duplicate implementations. So for example, in my case, I would have to do one implementation for the buffer class and another implementation for the buffer view class. I found that it also makes it very difficult to use those containers with any data type. So float and double usually work fine, but once you get past that, things tend to become more difficult. And again, I'll give an example of this in a second. The one exception to this is the clear function. So right now I have clear implemented as a member function. And the reason for that is that I can kind of keep track of the buffer state as far as whether or not it's clear. And that could allow me to do some optimizations elsewhere. I'm not doing that at the moment in my own code, but that's something I'm hoping to do in the future. And so having clear as a member function is pretty helpful for making that happen. So if I were to try doing a buffer with these math functions as member functions, it might look something like this. So I would have some apply gain function where I have some number t, and I want to multiply all of the numbers in my buffer by this number t. So if t is a floating point type, then maybe I could just do some vectorized multiply and multiply all of the numbers by the gain. But if t is not a floating point type, then maybe I need to do some kind of other operation. And so this is something that might work for a lot of types. We just do a standard transform. But the problem is that this expects that the multiply operator will be valid between whatever type x is and the type t that your gain is. And, for most math types, that will be true, but maybe you have some SIMD type where that's not true. And you need some other, you need to call some other function to get your multiply to work. I don't want that to prohibit you from using that type for a buffer class. So that's why these functions are not member functions. And so instead, I have this buffer math namespace, and I have a ton of functions in here for copying and applying gain and doing various things. And so just as an example, the same apply gain function, we have some buffer type, which is a template type. And then we have some gain, which is some float type, which hopefully will be the same type as the type in the buffer, but it doesn't have to be. And then there's an implementation of this that does what you would expect to do for most, math-like types. And so the idea here is kind of twofold. So one, this should work for any buffer type as long as it has kind of a uniform-ish interface. So it should work for a buffer view, a juice audio buffer, so on. But the other nice thing about this is that the buffer type itself doesn't actually need to be defined yet when this function is defined. So I can kind of decouple those two bits of code. So the idea, again, is just to try to make these buffer classes very easily extensible. So you can make a buffer or a buffer view with your own data types if you want. Hopefully the buffer math implementations will work for those data types. But if you need to do some specific math operations, either because, for example, the multiplication operator is not supported by your data type, or there's some optimization that you can do if you do something your own way, you can kind of implement those as you go. So you don't need to implement everything as soon as you try to use that class, like you would with a member function or a buffer that had math member functions. Instead, you can just wait until you actually need that function and then implement it. And it's really non-intrusive, so you never need to like fork or copy paste stuff, except as maybe like a base for the function that you want to implement for yourself. So for example, again, kind of the stupid example of making a buffer of strings. If you wanted to do that and have this apply gain function still work, you could just do it like this, where you basically create your template class for that buffer type. And then you could implement your own buffer math namespace and implement your own apply gain function. Whatever that means for your use case, I really don't know. But yeah, so really the idea here is that this would be useful for working with different types of SIMD wrappers and things like that. So hopefully that's useful for folks. Yeah, so finally, I wanted to talk a little bit about iterators. So if you've worked with audio buffers before, I'm sure you've written some code that looks something like this, where you want to iterate over the channels in your buffer, and then you want to iterate over all the samples in that channel, and you want to do something to each sample. So there's a few problems with this code. I mean, it's fine, it works, but it's not great, right? So first of all, it's kind of wordy. You've gone through, what, like 5 or 6 lines of code just to express something very simple. But even with all that wordiness, I don't find it very expressive, because you kind of have to dig through it a little bit to find what you're actually trying to say, which is, oh, I want to apply some function to all of the samples in this buffer. The second problem is that channel data is a raw pointer. So there's not really anything to stop you from just going past the end of it and doing something wrong. And you can implement some checks for that, but it's a little bit cumbersome to do that everywhere. And then once you go beyond kind of this simple case, things get a lot more complicated. Like if you want to iterate over subblocks of a buffer, or iterate over kind of the samples as the outer loop and the channels as the inner loop. So I was kind of thinking about this, and then I was thinking about Python. And for folks who are familiar with Python, you probably know about these enumerate and zip iterators that are pretty standard in Python these days. And these are kind of nice because with enumerate, you can get the index of the thing in your list as well as the thing itself. With zip, you can iterate over two lists simultaneously. So yeah, there's kind of some nice ways to do things very neatly and expressively in Python. And so you might think, well, can we do this in C++? And the answer is yes. It's just more complicated, I guess. So this is something that Bacon Paul showed me from the Surge Synth team. And the original author of this code is this fellow, Nathan Reed. He has a blog post about it, which I definitely suggest reading if you're interested in this kind of thing. So this is his implementation of an enumerate iterator in C++. And if we ignore all the complicated iterator stuff, this is how you actually use it. You just do a for loop over your index and your items, and then you can enumerate your vector and get both of those things. So it ends up being pretty neat and pretty similar to what you can do in Python. And so then my next thought was, well, let's do that for audio buffers. So this is a channels iterator for some buffer type. And the idea is that basically, as you go through the channels, for each channel, it will return a tuple containing the channel index and a span of the channel data. So I guess this is C++ 20, but you can make a C++ 17 version of it pretty easily as well. And so then when you go to use it, you can just say, okay, I want to iterate over the channels of my buffer. That'll give me my channel and a span over the channel data. And then I can enumerate that span and process each sample however I want. There's also a few other iterators that we worked out. So this is a samples iterator. So this iterates over the samples as the outer loop. This is actually something that Rachel Locke from the audio programmer implemented. So that's a nice way to do things. There's also a subblocks iterator. So if you want to iterate over like your buffer in blocks of 32 samples at a time, you can do that as well. And so the main idea here is just convenience. You can write your code more simply, more expressively, hopefully with fewer errors. And then, yeah, especially with loop bounds and thinking about where your loops start and end. At least for me, I found it easier to avoid bugs and crashes because of mistakes that I would make there. The downside is that iterators in C++ can be a pain to implement. So yeah, I mean, if you're interested in this stuff, definitely give it a try. It can be pretty fun. But if you're not interested in this stuff, then it's probably not worth the effort because it is kind of a lot of effort to do this sort of thing. So just to wrap up, at the moment, I have all of this code wrapped up in a Juice module, which is under the BSD license, and I have a link there for my repository, which has all of that stuff. I've been using this code in various forms and kind of gradually improving it over the last about year and a half now. So hopefully it'll keep getting better, and I'm sure other folks will have ideas for how to improve it as well. So I'm excited to see kind of how it continues to evolve. And yeah, just like a few takeaways as far as like lessons maybe that you've learned from this talk, hopefully. So first of all, it's good to understand your containers. It's good to know when something is owning versus non-owning. It's good to know when your containers might or might not allocate memory. Don't be afraid to write your own containers, even if you don't really want to use them. It's just like a learning experience. That's, at least for me, I found it to be really helpful in learning more about C++ and other languages as well. It's good to pay attention to memory layout. I didn't talk about it too much, but this has a pretty big impact on the performance of your software. So again, whether or not you're writing your own containers, pay attention to how the memory is laid out in those containers. And then if you want to have owning and non-owning containers, it's good to have a simple way to convert from the owning version to the non-owning version. If you're implementing functions for your containers, think carefully about whether you want them to be a member function or a non-member function. And then, yeah, iterators are great for making things more convenient and more likely to be correct if you can stomach the C++ way of doing them. So yeah, thanks for listening. If you want to get in touch, I'm on the Audio Programmer Discord, or I'm on email or GitHub pretty commonly. So yeah, feel free to reach out and chat. And yeah, hopefully I can answer some questions too.
Great. Thank you so much, Jatin. That was a very awesome presentation as always. So one of the questions that was earlier on in the presentation was just defining what real-time safe actually means. Can you just talk a little bit about what that means to you when you say real-time safe?
Sure, yeah. So I feel like kind of the most generic way to say it is like, if your code is real-time safe, you know how long all of the operations in your code are going to take. And so kind of more specifically, that means there's certain operations that you can't do, like a system call or allocating memory or locking, trying to acquire a lock or something like that, because those depend on things that are kind of out of your control and you don't know how long they're going to take. Yeah, I'm sure there's some more rigorous definitions out there, but that's kind of the way that I choose to think about it.
Yeah, that's always been my understanding as well. Deterministic is always the word that I always hear.
Yeah, well, deterministic can be tricky just because, like, for example, like if I have like a optimizing like equation solver or something like that in my code, like I don't know deterministically how long that's going to take, but I can kind of put a bound on it. So yeah.
Great. Not a loon asks, how could other data types other than float or double be useful as a buffer type?
Yeah, so recently I was working with something where I needed to use integers just because it was trying to do something that was emulating like an old video game console. And so I needed a buffer of like 16 8-bit integers or something. It was kind of weird, but that was useful. But probably the most common case for me is SIMD types. So I usually use xSIMD as like my SIMD library of choice. It's not perfect, but it solves most of my needs. And so instead of having a buffer of float, I'll have a buffer of like a batch of 4 floats or something like that. And it ends up working pretty similarly, kind of going back and forth between the two.
Awesome. And Matthew Yee King had a question that wasn't exactly on this topic, but more on the topic of machine learning. And he was interested in hearing your thoughts on audio programming with LLMs, large language model assistants. Do you have any views on that?
You know, I haven't used them very much, or at least I haven't really done much as far as like trying to use ChatGPT or something to like help my programming. I probably should. People have told me it can be very helpful for them. I think kind of mainly what I want is something that's a bit more personalized, where like instead of using something like ChatGPT, which is trained on, the whole internet's worth of code bases and so on, I think I'd prefer something that's like trained just on like my own code bases or like a few other code bases that I feel very confident about how they're implemented. So yeah, I was fooling around for a little bit with, I think it was called Private GPT or something, but I couldn't quite get it to work for me, so I gave up after a little bit. But yeah, I'd love to see more of that, and also like, for example, having a version of GPT that's just trained on like the JUICE documentation or like the eigen documentation or something, I think would be really handy. So yeah, I think for me, the stuff I find interesting is the stuff that's like hyper customized. I'm really excited about that stuff. Yeah,
that would be amazing. How about you, Damien? Have you used any LLMs in your coding adventures?
Yes. It kind of helps, for when it gets complicated in C++ for not so much like when you have a lot of templates and those fancy functions like enable if and stuff like that. I never really did the effort of learning all of that. So I'm using some AI like in Sea Lion to get this for me. And I think now that I understand it, I could redo it myself. So that's also a way of learning it.
That's awesome.
Yeah. There was a talk a few months ago by Marcus Hobbs, who talked a little bit about LLMs and use with Juice and with audio programming. And that was a great talk where he gives some tips on how to maximize your experience with those. And so if you're not aware of that, check it out. It's in our archives somewhere. Yeah, and I've had some experience with it as well. Just using it sometimes when I don't understand a particular piece of code and just trying to get a helping hand on certain things. It's been helpful, but like they always say, and like Marcus has said in his talk, use it with caution, because it's one of those things that it's important to know what's happening and what's going on. It's helped me a lot with CMake, actually. It's given me some good CMake help. So yeah, we all love CMake. Great. I think that's all the questions that we have. I'll give a couple more seconds. Just a reminder at the end to thank our sponsors, Focusrite and Sonux, for supporting the Audio Programmer Meetup. And also, if you'd like to join our audio programmer community, we have discussions like about this and much more. Join us on the audioprogrammer.com/community. We also offer development and recruitment services. Those are on the same website, theaudioprogrammer.com. So Jatin, Damien, thank you so much for your time and taking the time to put these presentations together. The slides for both of these talks are in the video description. Thank you so much for hanging out with us.
Thanks for having us.
Yeah.
Cool. As always, our audio programmer meetup is every second Tuesday of the month. Our next meetup will be October 10th. And as we're gearing up for the winter, and yeah, it's going to be a good time. Have some guests already lined up. Should be a really fun experience. For now, we'll go ahead and let you all go. Thank you to everybody who tuned in and was tuned in to us rather than the Apple presentation. Yeah, we hope to see you next month. Thank you, everybody, and see you next time. Cool. We're offline. Thank you.